Hello friends, in this video I am going to explain the B tree. It is a particular type of M-way search tree which has some of the given criteria which is written on the board beforehand. I will just explain those conditions which must hold for an M-way search tree to be a B tree one by one. And so our discussion on this in this video is about the B tree. So a B tree is a balanced tree, or a B tree is an M-way search tree which is of order M and which has the following criteria given in a point-wise manner on the board. So the number one point which should hold for an M-way search tree of order M to be a B tree of order M is that the root has at least two child nodes and at most m child nodes. So the root node of the B tree should have at least two child nodes, that is, there should be two pointers leading to the two subtrees from the root node, and that is the at least two child nodes case, and at most there can be m child nodes where order of the B tree is m. Suppose if the order of tree m is equal to 3, if the order is 3 where m is equal to 3, the root has at least two child nodes and at most it can have 3 child nodes. Or if the order is say about 5, the root has at least 2 child nodes and at most 5 child nodes, in this way. So the root has at least 2 child nodes and at most m child nodes for a B tree of order M, where B tree is nothing but an M-way search tree which should have these following conditions to hold on it. Number two is the internal nodes except the root. The internal nodes except the root have at least ceiling of m by 2 child nodes and at most m child nodes. What is that? The internal nodes, that is the nodes which are not the leaf nodes, and the nodes except the root. So the nodes which lie in between the root node and the leaf nodes, the internal nodes have at least ceiling of m by 2 child nodes and at most m child nodes. That is, if m is equal to say about 5, then it should have at least ceiling of m by 2, that is ceiling of 5 by 2. Ceiling of 5 by 2 means 5 by 2 is 2.5 and the ceiling function gives how much? That is the least integer which is greater than 2.5. That is 2.5 is 5 by 2 is 2.5, ceiling of 5 by 2 means 3. So the ceiling function applies over here, which means that it is the least integer which is greater than the fraction which is obtained by this calculation, that is 5 by 2. Suppose if we take the m to be 4, then it should be 4 by 2, 2, and that is the integer which is the least integer which can be greater than or equal to 2. Or in this case, since m is equal to 5, we will see that 5 by 2 is 2.5 and the ceiling function is nothing but the least integer which is greater than or equal to this 2.5, that is 3. So in a B tree of order M where m is equal to 5, we can have the internal nodes to be having at least ceiling of m by 2 child nodes and at most m child nodes. That is, in the case of 5, we could have a situation like the internal nodes are having 3 child nodes for the minimum case, and for the maximum case it can reach up to 5 child nodes. So this is the explanation of the number 2 point. Number 3 point says the number of keys in each internal node is 1 less than the number of child nodes, and these keys partition the keys in the subtrees of the node in a manner similar to that of M-way search trees. So you are quite familiar to M-way search trees, and in M-way search tree we have something like this. if we have suppose 3 key values, then we will have 4 child nodes like this. If we have 4 key values, that means if we have 4 key values, in that case we can have 5 child nodes. So always we see that in M-way search tree, we see that the number of child nodes is always one more than the number of keys in any node. So for an internal node in a B tree, because B tree is nothing but a particular type of M-way search tree, so in that B tree also we can see that the number of keys, that is, suppose this is K1, this is K2, this is K3, this is K4, and this is suppose A0, A1, A2, A3, A4. In this case, we see that these child nodes are 5 in number and the key values are 4 in number. So always we see that the key values are 1 less than the number of the child nodes. So what we have written over here is nothing but this type of situation is being written over here, and the keys and these keys partition the keys in the subtrees of the node in a manner similar to that of M-way search trees. That is, if we go towards this side, if we go towards this side, if we go towards this side, like this, we see if this K1 has 2 subtrees attached to it, that is the A0 and A1, that is the left subtree leads from A0, right subtree leads from A1. So in this case, we see that any value found over here, suppose any value found over here will be always less than the value of Q1. And any value found over here, suppose there are 2 values found from this A1 pointer, in that case, the values should all be greater than the value of K1. In this way, the keys partition the keys in the subtrees of the node in a manner which is quite similar to the case of M-way search trees. So this is the number 3 point. Number 4 point is that in case of M-way search trees, we didn't see this sort of point. This is a very special point to be noted in contrast to what we have discussed in the M-way search trees, because M-way search trees can contain leaf nodes which are not and on the same level. But in this B tree, since it is a balanced tree, all the leaf nodes should be on the same level. So all leaf nodes are on the same level. This is the point which is to be noted and which is quite exceptional for a B tree, which helps us to differentiate a B tree from a general M-way search tree. So all leaf nodes are on the same level. That is, all the leaf nodes should be on the same level in the B tree. So these are the explanation of the 4 points, which 4 criteria rather, which the M-way search tree will hold in order to be a B tree of order M. So after this, I am going to just draw a small B tree for the purpose of explaining the points over here by means of a pictorial representation. So before that, I am going to just wrap up this portion and get back to you with the pictorial representation with the explanation of that representation. So we have drawn a pictorial representation to make you understand what we are describing a bit ago. That is, B tree is a type of M-way search tree which looks like this. Suppose if we just analyze the B tree in a nutshell, we can say that this root node has 1 key value with 2 child nodes. The root node has 1 key value containing the value 48 with 2 child nodes. It leads to 2 subtrees. This is the one subtree, this is the other subtree. This is a B tree. Suppose this is the B tree which I have drawn is a B tree of order 5. So here M is equal to 5. So in this case, we see that the root node has one key value with 2 child nodes. This has 2 key values with 3 child nodes. This has 3 key values with 4 child nodes. In all the internal vertices except this leaf nodes and the root, we can see that the number of key values are 1 less than the number of the child nodes leading from them. So In this case, we see that there are 3 child nodes, there are 2 key values, there are 3 child nodes and 2 key values, there are 4 child nodes, there are 3 key values, and in this case we see that all the leaf nodes are located at the same level. That is, nothing we can see, no internal, no leaf node which we can see is on any other level other than the same level for each of the leaf nodes. So the values are like this. Suppose if we just, the partitioning is like this, that is 48 leads to some values on this side which should be always, these key values should be always less than 48. The partitioning is done in this way. Suppose this 48 leads to this right subtree which has values all more than this 48, all values are greater than 48, that is 56, 64, 84. In this way we can also see that this is also partitioned in a similar manner, that is 9, 18, 20 are all less than 31, and 36, 40 and 42 all greater than 31, these are all less than 45, and 46, 47 are greater than 45, and here we see this 49, 50 and 52 less than 56, and this 58 and 62 are greater than 56, 58 and 62 are less than 64, 67 and 75 are greater than 64, and 67 and 75 are less than 84, and 87, 88, 102 and 126 are all greater than 84. So the partitioning is done in a perfect manner as we have expected it to be, and this is the B tree of order M. And if we just analyze that, the first point, that is, the first point says that the root has at least 2 child nodes and at most m child nodes. That is, the root has at least, this is the at least case where we can see that the root has at least 2 child nodes, 1 child node, second child node. So this has 2 child nodes, the root has 2 child nodes. And in the internal nodes we have seen that all the key values are 1 less than the number of child nodes, that is okay. And number 3 point, the partitioning is done in a manner which we have explained it a bit ago. And for the number 4 point, that was which we were explaining in the sequence of the 4 points. The number 4 point was the leaves should be on the same level. So we can see that the leaves are on the same level. So this is a pictorial representation of a simple B tree of order M is equal to 5. And one thing is to be noted in connection with this explanation is that we can we have a situation like if a tree is called a 2-3 tree, there is a tree called 2-3 tree. So 2-3 tree is nothing but is a B tree of order is a B tree of order 3. Suppose a 2-3 tree is nothing but is a B tree of order 3. So it can have how many? It can have how many child nodes? It can have 2 or 3. It can have internal nodes. Since there are, how many internal nodes can there be in a 2-3 tree? Suppose it is a order of B tree of order 3. Suppose I can draw this B tree of order 3 in this way. Suppose this one. Suppose this one. So this can be a B tree of order 3. So here we see that suppose there are also like this, here can also be like this. We can see that all a similar type of things can be extended in other portions. I am not drawing the full figure. I am just making you understand that 2-3 tree gets the name from this situation, that all the internal nodes have at least 2 child nodes or 3 child nodes. Suppose in this case we see, suppose we can have this to be deleted to make you understand. Suppose this portion. So this portion has 2 key values, 3 child nodes, internal node, and this internal node has 1 key value and 2 child nodes. So the minimum which we can achieve is nothing but we have described that the minimum can be achieved is ceiling of m by 2. That is ceiling of m by 2 for 3 by 2 is ceiling of 1.5. That is ceiling of 1.5 is 2. So minimum there should be 2 child nodes, 1, 2, and maximum it can reach up to m child nodes, that is 3 in case of a B tree of order 3. So this sort of tree which has this sort of B tree which has an order of 3, which can have internal nodes to have maximum of 3 child nodes and minimum of 2 child nodes, can have 2 situations for the number of child nodes. There can be 2 values only for the number of child nodes, that is 2 or 3, and for that it gets its name in this way, that is a B tree of order m is also called a 2-3 tree. So this is all about the overview of a B tree, and if you have any doubts and queries pertaining to this entire explanation, you can well post your doubts and queries into the comment section below so that I can address them. Thanks for watching this video.